Hello everyone, myself Dr. Harish Belga, Associate Professor in the Department of Electrical Engineering, Vardhaman College of Engineering. Today I am going to discuss the first topic in the course Fundamentals of Electrical Engineering. The title of the topic is Electrical Circuit Elements. Before starting this course, I assume that the listeners are aware of the terms electron and charge, and the charge of an electron is minus 1.6 into 10 power minus 19 coulombs. Starting with few basic definitions. The first one is current. Current is nothing but rate of flow of electrons in a conducting path or rate of change of charge. This is represented with the letter I equal to dq by dt, where q is the charge and t is time. The units for this current are coulomb per second or amperes, or in short called amps. The current is associated with magnitude and direction. That means for any element the current is represented like this. If this is the element, and current will be represented with an arrow mark like this, and a magnitude something like 10 amperes. Right. This current can be either DC or AC. DC stands for direct current, where the magnitude of current is independent of time. That means in a circuit the current can be represented to vary like this. That means it is constant throughout certain period of time when all other parameters are constant. This is DC. When it comes to AC, the current is expected to alternate between positive and negative values. The center average is 0, and it is expected to vary between Im to minus Im. We will study in detail about AC current later. For now, I am sticking to only DC concepts. The next term is voltage. Voltage is nothing but electromotive force that drives the current to flow in a closed circuit path. However, there is no necessity for a closed path for voltage to exist. Generally, current is said to flow through an element, whereas voltage is said to be existing across 2 points in a circuit. The basic definition of voltage is nothing but work done per unit charge. That means it is the work to be done to move a charge from one point to another point. So, the units of voltage are volts or joules per coulomb, and it is represented by W by Q, where W is the work done and Q is the charge. This is also called as potential difference. The voltage or potential difference is associated with magnitude and polarity. That means while representing a voltage, say for example, this is the element in which voltage is across which voltage is existing, it is represented as a plus a minus on either side, and a voltage value like say 10 volts is also given. So, it is associated with polarity and magnitude. Proper polarity indication is necessary. The next term is power. Power is nothing but rate at which work is done. This is also a simple product of voltage in current in DC networks. The units of power are joules per second or watts. P equal to V into I watts, which in short can be written as dW by dt, rate of change of work. The next term is energy. The capacity of doing work of any object or quantity is called energy. Units for power are joules or watt hours. Energy is nothing but product of power into time. The next term is a network. Network is an assembly of circuit elements. For example, let us take this one. I am taking two resistors in series and one resistance like this. So, this can be called as network. There is no necessity of any sources to be connected, and there is no necessity of any closed path for a network. The next one is circuit. If the assembly of circuit elements consists of at least one closed path, then that network can be called as a circuit. For example, if this is network, I am adding one line here and I am connecting one source here. We will discuss about source in detail later. Sorry. Okay. Now, current can flow through this network in this direction. So, this can be called as a circuit. A node is a point through which a circuit element is connected to the circuit. That means, this can be a node, this is one node, this is another node. Okay. Like that you can identify more nodes. Let us name them as A, B, C and D. This is E, this is F. Okay. So, all these A, B, C, D, E, F are called nodes. The next one is branch. The path from one node to another node in a circuit is called a branch. Let us take these two nodes here, A and B. So, if A and B are two nodes, any element between those two, there can be multiple elements between these two nodes. So, any one element one or more elements which are connected in series between A and B is called a branch, right. The next one is loop. Loop is any closed path going through circuit elements. Just like I mentioned about circuit, which requires at least one closed path. So, one circuit can have multiple closed paths. That means, one circuit can also have multiple loops. Any closed path in a circuit is called a loop. Now, in any network, the elements can be connected in two ways. One is series connection, and the one is parallel connection. For any two or more elements to be connected in series, there should be constant current flowing through all those elements. For example, this one, this is, let us say, R1, and I am connecting another resistor R2. Okay. So, another resistor R3. Okay. The resistors R1, R2, R3 are said to be connected in series because any current flowing through R1 will also flow through R2 and will also flow through R3. The current amount of current flowing through these three elements, if any source is connected to these networks, the amount of current flowing through these three elements is same. Okay. In other words, we can say that if two elements are connected at only one terminal of the element, then it is called series connection. The condition is there should not be any other element to be connected at the same connecting point or node. Okay. For example, if I connect another resistance R4, then we cannot call R1 and R2 in series. Okay. Here only R2 and R3 are in series, but R1 and R4 are not in series connection. The next one is parallel connection. Say for example, if I am connecting one more resistor here across R3, let us say that is R5. Okay. That means I am connecting these two elements R3 and R5 on either side of the element. That means both terminals of the both elements are connected together. So, this type of connection is called parallel connection. In parallel connection, the voltage across those connected points is constant. That means voltage across R3 and voltage across R5 are constant. That means in series connection current is constant and in parallel connection voltage is constant. Now, let us classify different types of elements that we use in electrical circuits. The first classification type is active elements and passive elements. Active elements are capable of delivering power to some external devices. Okay. Most of the time we treat sources as active elements. Apart from these sources, we can also consider those elements which can convert one form of energy into another form, like transducers can also be called as active elements. Few examples of active elements are battery, transducer, voltage and current sources. The next category is passive elements. Passive elements are those which are capable of absorbing power or receiving power. Some passive elements like inductors, capacitors, resistors, not resistors, inductors and capacitors can store energy and deliver back when necessary, or they can release the stored energy. However, they are storing in the same form of energy, that is electrical, either electrostatic or electromagnetic. They are not converting the form of energy. So, these elements are passive elements. Some listeners might get a doubt that how can a battery be treated as passive element, active element, when this is also storing energy. Battery stores energy in chemical form. That means it is converting that electrical energy into chemical, and then when it is necessary, it is converting the same chemical energy back to electrical energy and delivering to the load. Okay. That is the reason battery comes under active element, and this capacitor and inductor comes under passive elements. Next classification is linear and non-linear. Any electrical element, if it is to be called as a linear element, the relation between excitation and response given to that element should be linear. That means linear is nothing but a straight line. For example, let us take a resistor whose relation between voltage and current varies linearly. That means if current is flowing through any element, the voltage developed across that element is linearly proportional to the current flowing through that element. If we increase current, voltage also increase, or the other way, if we increase voltage, current flowing through the element also increase, or if you decrease the voltage, current flowing through the element also decreases. People often confused with the definition as definition of linear elements as the relation between voltage and current. For most of the elements it is true, but not all elements like inductor and capacitor. The relation for inductor and capacitor between voltage and current is non-linear. However, as the voltage excitation and response in those elements are not voltage and current, so they are still be called as linear elements. We will discuss in detail about the linearity of capacitor and inductor in next classes. Then any element whose relation between this excitation and response is non-linear, then that element is called a non-linear element. So, in the earlier example, voltage is the excitation and it is producing a current. So, current is the response. Okay. In more formal definition, any linear element is said to follow superposition theorem. Also, it follows homogeneity and additivity properties. So, we will discuss again these properties in next classes. The next type of classification is unilateral elements and bilateral elements. If the voltage current relation or the excitation and response relation in any element is same in both the directions of that element, then that is called bilateral element. and if the relation is different depending on the way we are connecting the element, then that is called a unilateral element. That means the current flowing in unilateral element in one direction is different from the current flowing in the opposite direction. The example for such unilateral elements are diodes. Okay. So, in diodes, the current flowing in one direction is not same as the current flowing in another element. Also, the diode is another example for non-linear elements, because the relation between voltage and current of a diode vary something like this, right. Bilateral elements are those where voltage current relation is same in both directions. For example, resistor. You can connect a resistor or inductor in any direction. Even if you interchange the terminals of resistor or inductor, there will not be any effect on the circuit elements. The next classification is lumped elements and distributed elements. Lumped elements are generally small and electrically separable for any analysis purpose. Examples are like resistors, capacitors, inductors, transformers, motors. Okay. The properties of these elements can be analyzed individually, whereas the distributed element are those which are not electrically separable for analytical purpose. For example, transmission line whose length vary from some 50 kilometers to 400 kilometers, something like that. In transmission lines, the resistance, inductor and capacitance of the transmission line are distributed throughout the length of the transmission line, and it is difficult to exactly replicate the properties and analyze in individual small elements. Now, let us start in detail about few basic elements, starting with the sources. As I mentioned earlier, voltage source and current source are active elements, whereas resistor, inductor and capacitor are passive elements. Voltage source and current source, these can be ideal or practical. However, while simulating or while analyzing the properties of these elements, we consider them to be ideal. However, in practical case, their properties change a little. How they change, we will discuss now. For any voltage source, a voltage source is one element which delivers constant voltage irrespective of the amount of load. Okay. As of now, I am talking about ideal voltage source. Okay. For example, this is 10 volts voltage source. Okay. The symbol of a voltage source is written like this. This is DC voltage source. This also represents a battery. Okay. Just a minute. Right. So, another representation of voltage source, DC voltage source, is plus and minus inside a circle. Okay. This is another representation. You can use any one of these two. Either way, it is a DC voltage source. Especially when you want to represent a battery, we use the first representation. Okay. So, an ideal voltage source is expected to deliver constant voltage for any amount of connected load. Okay. Constant voltage of V. So, this is independent of the amount of load connected. Here, by the word load, I mean anything like a bulb, a fan, a motor, which absorbs power from the source, mostly a passive element. Okay. Now, this is ideal characteristic. However, practically voltage sources tend to decrease the value of voltage as the load increases, like this. So, this is ideal and this is practical. So, in a practical voltage source, the voltage tend to decrease as the current increases. Current increases with the amount of load. Why does this voltage reduce? In practical case, apart from the simple voltage, there will be some amount of internal resistance like any other object in this world. Every element has certain amount of internal resistance. Now, if we add that internal resistance to the circuit, okay, so that internal resistance can be series or parallel. For in the case of voltage source, whether it is series or parallel, we will see now. Let us say I am adding this internal resistance as R int in parallel with voltage source. As I mentioned earlier, in parallel connection, the voltage is constant in all the elements that is connected in parallel. So, as in practical case, as I mentioned, the voltage decreasing, so this cannot be the case. So, the internal resistance of any voltage source will be represented as a series connection like this. So, 10 volts and let us say this is my R internal. Okay. So, this R internal which is nothing but the internal resistance is represented as a series connection with respect to the voltage. As the current increases, the voltage drop across this RIN will be RIN into I. If the current is I, okay, the voltage drop across this RIN into I, that will be increasing. So, the resultant voltage appearing across the terminals A and B will be less than 10 volts, because some amount of voltage is dropped across this resistance, something around, say for example 1 volt. It not in the range of 1 volt, something around some 0.5 volts. As the current increases, this voltage also increases. Okay. Similarly, for current source, again there can be an ideal source or practical source, but most of the current sources are practical only. In reality, we see only voltage sources in physical form, but there exist some current source also. For example, some examples of current sources are driver circuits, the circuits which we use to drive LEDs, which we use to drive stepper motors. All those driver circuits deliver constant current irrespective of the voltage applied across that. Okay. So, the current sources are represented like this. Okay. Make sure that you are drawing a perfect circle inside which a straight arrow, okay, a tilted arrow will represent another measuring device. So, do not write a tilted arrow. So, it should be a straight line. Okay. So, current source is expected, an ideal current source is expected to deliver constant current I irrespective of the voltage applied across it or any other source or element connected in the circuit. However, in practical applications, if let us say this is the ideal current, okay, with any amount of voltage. So, practically it will go like this, just like voltage. The reason for this is again internal resistance of this current source. Okay. So, in the case of electrical current sources, the internal resistance is represented in parallel with the current source, okay, because if there are parallel connections, current will split into two parts at this node. Okay. So, if there is a current of 10 amperes for example, from the actual current source, some amount of current will flow through this resistor, okay, say for example 1 ampere. Okay. So, if 1 ampere is flowing through this resistor, the remaining current given to the load okay, this will be only 9 amperes. Okay. So, in place of expected 10 amperes, it is receiving, the load is receiving only 9 amperes because of the internal resistance, which is consuming some amount of the current that is delivered by the actual current source. Okay. So, this is the characteristic of ideal voltage source and ideal current source. Okay. The straight line here is ideal current source and the bottom one is practical. Okay. Right. So, with this I am stopping this class here. We will discuss about other elements in the next classes. Thank you.